Welcome dear students once again into the class of number theory, and we will continue here with the chapter of continued fractions. And in this video lecture we will see what are Pell's equations, what are the solution of a Pell's equation using continued fraction, etc. So first of all, let us see what is a Pell's equation. So any equation of the type x square minus dy square is equal to 1, where d is a positive integer, d is a positive integer, not a perfect square, not a perfect square, is called a Pell's equation. So this is your Pell's equation, x square minus dy square is equal to 1. D is a positive integer which is not a perfect square. So such an equation can be solved using continued fractions. How to solve it? What are the solutions? This we'll learn in this lecture. The first theorem, what we are going to prove here is that if P and Q are positive integers, P and Q are positive integers such that P square minus dq square is 1. So that means P and Q are the values of x and y. That means PQ is a solution of the Pell's equation x square minus dy square equal to 1. So if PQ are positive integers such that P square minus dq square is 1, then this solution P and Q, then this solution P and Q will give you a fraction P upon Q, and this fraction P upon Q is a convergent of continued fraction expansion of under root d. This we will prove, but before proving this theorem we will have to prove one lemma which will be used in the proof of this theorem. So let us see what the lemma is. I am putting a border here because this I am not going to prove. Before proving this theorem, I will state and prove one lemma. So what this lemma is? This lemma says that if xi is an irrational number, if xi is an irrational number, and if there exists a rational number, if there exists a rational number a upon b, GCD of a and b is 1, that means a upon b is in its lowest form, b is greater than 1, greater than or equal to 1, such that mod of xi minus a upon b is less than 1 upon 2b square, then a upon b is a convergent of, then a upon b is a convergent of continued fraction expansion of xi. So this we will prove first before going on to this theorem. So we are given that xi is an irrational number, and we are also given that there is a rational number a upon b in its lowest form with b greater than or equal to 1, such that xi minus a upon b mod is less than 1 upon b 2b square. This is given to us, and we have to show that a upon b is a convergent of the continued fraction expansion of xi. We will prove it by method of contradiction. So let a upon b be not a convergent of continued fraction xi. And we know that the convergence of xi, an irrational number, we usually write them as Pn upon Q1. So that means A upon B is not equal to Pn upon Q1 for any n. So that means A upon B is not equal to Pn upon Q1 for any n. A upon B, that is this rational number which we are using for xi minus A upon B mod is less than 1 by 2 b square, which is given to us. We have to prove that this is a convergent of the continued fraction expansion of xi. We have supposed that it is not a convergent of continued expression of xi. So that means A upon B is not equal to any convergent. Any convergent means in general you can say nth convergent. So it is not equal to that. Okay. Now one thing is clear, that your Q1, your B is greater than or equal to 1. This is given. B is greater than or equal to 1. And we know that Q1 is an increasing sequence. This we have already proved in our previous videos, that Q1 is an increasing sequence. That means there must exist some n such that there must exist n belonging to n such that your B lies between Q1 minus 1 and Q1. That means your B lies between some two consecutive Q1s, and automatically A will also be lying between Pn minus 1 and Q1, the numerators of corresponding nth convergence. Also, your B is greater than or equal to 1, so you can say from here that 1 is less than or equal to B is less than Q1 also. You can also say this. And now, using this and the fact that A also lies between Pn minus 1 and Pn, we can say that from these three, we can say that mod of Q1 xi minus Pn is less than or equal to mod of B xi minus A. We can say this using the given facts. Now, from here, B xi minus A upon B. We know that xi minus A upon B is less than 1 by 2 b square. So taking B outside, B is positive number, so can be taken out from this modulus. So it is B xi minus A upon B, and this xi minus A upon B is less than 1 by 2 b square. So it is less than B into 1 upon 2 b square. 1 b will be cancelled from numerator and denominator, and it will become 1 upon 2b. So I am directly writing that Q1 xi minus Pn is strictly less than 1 upon 2b. So this is strictly less than 1 upon 2b. This is one thing. Another thing, that xi minus, from here, once again, you can take Q1 outside. Q1 is also a positive number, so can be taken out. So you can write it Q1 mod xi minus Pn upon Q1 is less than 1 upon 2b. And since Q1 is a positive integer, its reciprocal will be a positive number. So you can multiply this inequality both sides by reciprocal of Q1. So what will happen? Q1 will be removed from here, and here you will get 2b into Q1. So we have that xi minus Pn upon Q1 is less than 1 upon 2b Q1. This is one thing. I'll keep it here. I'm rewriting it as xi minus Pn upon Q1 is less than 1 upon 2b Q1. This is one result which we will use. Now, B, A, B, Pn, Qn are all positive integers, and since our A upon B is not equal to Pn upon Qn, that means Bpn is not equal to Aqn, and this means Bpn minus Aqn is not equal to 0. B is integer, Pn is integer, A is integer, Qn is integer. So this combination is an integer which is not equal to 0. An integer which is not equal to 0, its mod will definitely be greater than or equal to 1. So mod of this is greater than or equal to 1. Mod of this quantity is greater than or equal to 1. Reciprocating both sides, what you are going to get is that 1 is less than or equal to, no need to take reciprocal. In fact, I need 1 upon bk1. So 1 upon bk1, multiply both sides by 1 upon bk1, and I am writing right hand side first, and then this less than or equal to will become greater than or equal to. So 1 upon bk1, when you will multiply these two, less than or equal to will become greater than or equal to, and here you will get mod of Bpn minus Aqn upon Bk1 is further this greater than or equal to will become less than or equal to, and now separate these two, it will become mod. When you will take Bpn upon Bk1, B will be cancelled, you will get Pn upon Q1 minus, similarly here you will get A upon B, and here I am introducing xi, Pn upon Q1 minus xi plus xi minus A upon B, and now using the fact that mod of A plus B is less than or equal to mod A plus mod B. So this is less than or equal to mod of xi minus Pn upon Q1 plus mod of xi minus A upon B. Xi minus Pn upon Q1 mod is less than 2bq. So this is less than 1 upon 2bqn plus xi minus A upon B mod is already given to be less than 1 upon 2b square. So it is 1 upon 2b square. What you have obtained from here. So once again it is time to rewrite these steps. So rewriting, you will get 1 upon bk1. One thing is to be noted that b is in the denominator here, b is in the denominator here, b is in the denominator here. So you can multiply this inequality, this and this throughout by b. B is a positive number, so there is no problem. B is given to be greater than or equal to 1. So no problem, you will get here 1 upon q1, 1 upon q1 strictly less than 1 upon 2q1 and plus 1 upon 2b. Take this 1 upon q1 to the left hand side, you will get 1 upon q1 minus 1 upon 2q1 is strictly less than 1 upon 2b, and 1 upon q1 minus 1 upon 2q1, it will become 1 upon 2q1. So 1 upon 2qn is less than 1 upon 2b, multiplying by 2, 1 upon q1 is less than 1 upon b, and now reciprocating, you will get q1 is greater than b. That means b is less than q1, which is a contradiction, because in the starting we have seen that q1 minus 1 is less than or equal to b is less than q1. So this is a contradiction, and why this contradiction is there? Because we have supposed that this number a upon b is not a convergent of the continued fraction expansion of xi. So that means a upon b must be a continued fraction expansion of this xi, irrational number. Now we will move on to the proof of the main theorem. This was the proof of the lemma, And now we are moving on to the proof of the main theorem. For the main theorem, we are given that p and q are positive integers such that p square minus dq square is 1. That means pq is the solution of the Pell's equation x square minus dq square equal to 1. And we have to show that p upon q is a convergent of the continued fraction expansion of under root d. Starting from here, this is p square minus dq square is 1. So you can factorize it as p minus under root dq into p plus under root dq is equal to 1. Take this to the right hand side. That means p minus under root dq is equal to 1 upon p plus under root dq. And multiply throughout by 1 upon q. So multiply throughout by 1 by q means you are dividing both sides by q. Q is non-zero, so no problem. Separating now, p upon q minus under root d is equal to 1 upon q p plus under root d q. Now look that p positive, under root d is positive, q is positive, this q is positive, so the right hand side is a positive number. And if right hand side is positive, left hand side must also be positive. So that means what we have obtained, that this p upon q minus under root d is positive. This is our first step. And now once again here p square is 1 plus dq square from here, and it is definitely greater than q square. P square is greater than q square gives you p is greater than q. P is greater than q, so p plus under root dq is greater than q plus under root dq. Adding under root dq both sides. So p plus under root dq is greater than d plus under root dq, and under root d is greater than 1. So this is greater than q plus 1 into q, that means 2q. So p plus under root dq is greater than 2q. Now reciprocating both sides, 1 upon p plus under root dq is less than 1 upon 2q. In an earlier step which I have removed from here, we had p minus p upon q minus under root d was equal to 1 upon q p plus under root dq, if I am not forgetting. This was the step. And 1 upon p plus under root dq is less than 2q. Use it here, so it will become less than 1 upon q into 2q. So this p upon q minus under root d is less than 1 upon 2q square. Also, this p minus q upon p upon q minus under root d was positive, so you can put a mod here because it is a positive quantity. So mod of this quantity is less than 2q square. And by the lemma which we have just proved, if p upon q minus under root d is less than 1 upon 2q square, then p upon q must be a continued, some convergent of continued fraction expansion of this under root d, which was required to be proved in this theorem. So we have proved that if pq is a solution of the Pell's equation x square minus dy square, then the solution p upon q is a convergent of the continued fraction expansion of under root d. Moreover, there is remark that if you are given that x square minus dy square is 1. This Pell's equation is given, and in the continued fraction expansion of under root d, it will definitely be a periodic expansion. If the length of the period, if the length of the period of continued fraction expansion of under root d is, if the length is even, then your solution will be Pn minus 1 Qn minus 1. And if the length of the period is odd, then solution will be P2n minus 1 Q2n minus 1. So this is an important point to be kept in mind, that when you will expand this continued fraction under root d, it will definitely be recurring, and if it is recurring, then definitely there will be a term which will occur again and again, like under root 7. If you see, it is, I think, 2 1 1 1 4. It is this, if I am correct. I don't know, it may be wrong. If I am correct, then this is under root 7 is equal to this, and this is the portion which is being repeated again and again, and this is the period. So what is the length of the period here is 1 2 3 4. Since the length of the period is 4, even, the solution will be this. And what is the length? N is 4, so the solution will be P 4 minus 1 Q 4 minus 1, that means P3 Q3. That means the third convergent will give you the solution of this Pell's equation, x square minus 7y square is equal to 1, because here I am using under root 7. If it is not clear, no problem, we will move on to some questions, we will have some examples, and then it will be clear to you to how to find the convergent which will give you the solution of the Pell's equation, x square minus dy square is equal to 1. So let us have some questions. I'll try to take one question for even expansion, length to be even, and one example with length to be odd. So let us have two examples. First, find the solution of x square minus 13y square is equal to 1 using continued fractions. This is the Pell's equation, and we will solve this Pell's equation using continued fractions. So how to solve it? First of all, we have to find the continued expression of under root 13. So how to find it? I am going to start it. Under root 13 is equal to, what is its integral part? The integral part is 3, because it is greater than the square of the 3 and is less than the square of the 4. So its integral part is 3. I am going to write 3 plus under root 13 minus 3. And if you have seen the previous video, you know what to do next. You take this under root 13 minus 3 in the denominator. So it will become 1 upon under root 13 minus 1 upon under root 13 minus 3. And then rationalization process starts. Rationalization will give you under root 13 plus 3 here, and divided by 13 minus 4 is 9 is 4. And once again, this under root 13 means 3 plus 3 point something. 3 point something plus 3, 6 point something. 6 point something divided by 4 means integral part is 1. So I am writing 1 plus and minus 1. When I am writing minus 1, I am to solve this portion by taking LCM. Taking LCM, 4 you will get minus 4 here, and 3 minus 4 will become minus 1. And once again, take this 13 minus 1 upon 4 into the denominator. So taking this into the denominator, 13 minus 1 by 4. 13 minus 1 by 4. This is 4 upon 13 minus 1. And now once again the same process, rationalization. So rationalization, you will get here 4 under root 13 plus 1, and in the denominator 13 minus 1 will become 12. So you will get 12 here. This 4 and 12 will be cancelled, so you will get 3. You will get 13 under root plus 1 upon 3. And repeat the process. Under root 13 means 3 point something. 3 point something plus 1 means 4 point something. 4 point something divided by 3. Once again the integral part is 1. So it is 1 plus minus 1. And repeat the process. Take the LCM. Taking LCM here 3, you will get minus 3 here, and 1 minus 3 will become minus 2. And once again, what you have to do? You have to take this to the denominator. This 13 under root 13 minus 1 by 2 will go into the denominator of the denominator. And once again the same process. That means rationalization. Under root 13 plus 2. In the denominator, you will get a square minus b square means 13 minus 4, that is 9, and will be cancelled. 3 and 9 will be cancelled to give you 3. You will be left with this term now. And repeat the process. This is 3 point something. 3 point something plus 2 is 5 point something. 5 point something divided by 3. Once again, the integral part is 1. So it is 1 plus and minus 1. And you know what to do next. Once again, take 3 as LCM. Taking 3 as LCM, you will get minus 3 here. 2 minus 3 will become minus 1. And this 13 minus 1, under root 13 minus 1 will go into the denominator of the denominator. So you will get here 1 upon under root 13 minus 1. Once again, the rationalization process, under root 13 minus 1, and in the denominator of the denominator you will get 13 minus 1, that means 12, and this 3 and 12 will be cancelled to give you 4 in the denominator, so you are left with this now. And once again, it is 13 plus 1, sorry. Under root 13 means 3 point something. 3 point something plus 1. 4 point something. 4 point something divided by 4. That means 1 point something. So once again, you will get 1 here plus and minus 1. The process will be continued. And let me see from the book what the final expansion will be, because you know how to get the final expansion when it will be repeated. We will stop it here. From the book, I am having here the book. That is from the book I can see what is the value of under root 13. Under root 13, its continued fraction expansion is being given here. So let us see what is the value of the continued fraction expansion of under root 13. I am unable to find it here. Just checking. Under root 13. Yes, under root 13 is 1, then 1 1 1 6 periodic. This is the value of under root 13. If this is the value, then look at what is the period. This is the period. Length of the period is 4, and if length of the period is 4, then the solution will be given by P 4 minus 1, Q 4 minus 1. That means P3 Q3. And how to obtain now P3 Q3? You start with K, then AK, PK and QK. K is 0, 1, 2, 3, because we want P3 Q3. So I am going to stop it here up to 3. What are your QKs and PKs? for QK and PKs, you note that it is, this value is, this is not 1, this is, sorry, 3, because the integral part must be 3. Integral part, this is 3. And now these are the values what I am taking here. This is 3, AK is 3, then it is 1, 1, 1, next is 6, but is no use because I want to read up to P3 and Q3, only P3 and Q3 are required. Then this 3 will be here, this 1 will be here, this 1 will be here, and here you will get 3 into 1, A0, A1 plus 1, 3 into 1, 3 plus 1, it is 4. And next, to obtain, multiply these. Next is the process which is easy. 1 into 4 is 4 plus 3. 4 plus 3, 7. Similarly, 1 into 7, 7 plus 4, 11. I am not going further, but even if it is required, then it is 6. The next will be 6 into 11, 66 plus 7, so 73, and the process will be continued. And the same process will be for Q case. 1 into 1 plus 1. So 1 into 1 is 1, plus 1 is 2. Then 1 into 2. 1 into 2 is 2, and plus 1 is 3. So you have reached to the solution. Solution is here, 11 and 3. Your P3 is 11, your Q3 is 3. So your final solution is 11, 3. This will be the solution of this Pell's equation, x square minus 13y square equal to 1. If this is correct, because this I have just taken from the book, if it is correct in the book, the solution is okay. If there is some problem, then the process you know now, how to obtain it. If it is not this, it is something else, you know how to find the solution. Suppose here is some number. Suppose here is some number D. Suppose here is some number D. And for this D, suppose your continued fraction expansion gives you 5, 1, 2, 4, and this is the period. Here the length of the period is 3. And if the length of the period is odd, length of the period n is 3, it is odd, your solution is P 2n minus 1, Q 2n minus 1. That means it is 2 into 3, 6 minus 1, P5, Q5. So your solution will be from the fifth column of your table. So how to obtain the table now? In this case, suppose for D, this is your continued expansion, then how to obtain the table? You will get K, and this time your K's will be 0, 1, 2, 3, 4, 5, because we need P5 and Q5. Then you will have your AK's. Your AK's are 5, 1, 2, 4. 5, 1, 2, 4, 1, 2, 4, 1, 2, 4. It will be repeated. What are your PK's and QK's? Your Q naught will be 1. It will be 5. Here you will get 5 into 1 plus 1, 6, and this will be 1. These two are, you know, because your P naught is equal to A naught, your Q naught is equal to 1, your P1 is A naught into A1 plus 1, and your Q1 is equal to A1. This is known. Now next is the process. So 2 into 6, 12, plus 5, 17. Then 4 into 17, 68, plus 6, 74. Then 1 into 74, 74, plus 17. So it is 91. Then 2 into 91, 182 plus 74. So 182 plus 74 will be 256. And apply the same process to find the values of your Q case. It will be 2 into 1, 2 plus 1, it is 3. 4 into 3, 12 plus 1 is 13. 1 into 13 is 13 plus 3 is 16. 2 into 16 is 32 plus 13 is 45, and your solution is P5Q5, so it is 256:45. So this is the solution of this Pell's equation. So with these solutions of Pell's equation, I am going to end this chapter continued fractions here. In the next video we will meet with some other chapter of the number theory, maybe pair fractions. Till then, thank you once again.